Welcome to part 2 of automobile brake horsepower, foot-pounds torque, and brake thermal efficiency on a moving automobile, applicable to the 2012 Chevy Impala. We will now move into the actual applications analysis of these variables on this given vehicle. First problem. What is the maximum brake horsepower of this given 6-cylinder, 4-stroke, gasoline-powered automotive piston engine when operating at its maximum rated torque in foot-pounds? We need the bore and stroke, the Planck formula over 33,000 for brake horsepower, the maximum rated torque in foot-pounds, the displacement in cubic inches. So we start with converting the liters displacement to cubic inch displacement. 3600 cc's is 3.6 liter times 0.061, so 219.6 cubic inch displacement, CID. We have a maximum torque rating in foot-pounds of 262 foot-pounds at 5,300 RPM. So the ratio between the torque and the cubic inch displacement times 150.8, that translates to 180 pounds per square inch pressure exerted on the piston during each power stroke. Stroke of 3.37 inches divided by 12.28 feet stroke length. Piston head area, bore diameter 3.7 inches divided by 2, radius squared times pi, 10.75 square inches piston head area. 4-stroke, piston reciprocating engine at 5,300 RPM divided by 2 equals 2,650 power strokes per minute, and we have 6 cylinders. So when we multiply all 4 out and divide it by 33,000, that translates to 261 brake horsepower when at maximum rated torque of 262 foot-pounds at 5,300 RPM. So now we know the maximum brake horsepower output. The specs indicate a 300 indicated horsepower output at 6,800 RPM, but that's not relevant to the actual power output. It's the brake horsepower you must focus on, which is directly proportional to the BMEP and the foot-pounds in torque, which must be at a given RPM. Now, assume that this vehicle starts at 0 miles per hour rest and accelerates to a final speed of 70 miles per hour. How much horsepower would it require to allow this acceleration over a time span of 6.5 seconds? Convert the pounds weight of the vehicle into kilograms. Convert the miles per hour to meters per second. 70 times 22/15 divided by 3.28. 70 miles per hour is 31.3 meters per second. Time, 6.5 seconds. So multiply the mass in kilograms times the final speed in meters per second, quantity squared, divided into 2 times 6.5 seconds. That translates to 121,783 watts divided by 746. So that's 163.25 horsepower to facilitate this particular acceleration. So let's say the observed RPM during this acceleration on the tachometer was 3,800 RPM. You would simply take the brake horsepower required to facilitate the RPM times 33,000 divided into the average RPM during the acceleration times 6.28, That would translate to 226 foot-pounds of torque. To facilitate this acceleration of 0 to 70 miles per hour in 6.5 seconds with a required brake horsepower of 163.25 bhp. Now assume this automobile is on dry level ground, driving through 59 degree Fahrenheit air temperature on a elevation of 880 feet above mean sea level, and it maintains a steady 70 miles per hour cruise speed, has a projected frontal area of 17 square feet. Calculate how much horsepower is required to keep this automobile at a steady cruise speed of 70 miles per hour at 0 acceleration and 0 deceleration. The only forces opposing the automobile's inertia at steady speed of 70 miles per hour are aerodynamic drag and tire rolling resistance. So we need to first calculate the horsepower required to overcome aerodynamic drag, which would be started by knowing the atmospheric pressure at the given elevation. So all we do is take 880 divided into this value, take this quantity, subtract it from 1, and then take that value and take it to the 5.255876 power times 14.7 at 880 feet above sea level. The atmospheric pressure is 14.24 psi. Next, convert the outside air temperature from Fahrenheit relative temperature to Rankine absolute temperature, and all you do is add 460 to the Fahrenheit temperature to get degrees Rankine absolute temperature. Next, calculate the air density in slugs per cubic foot. You would take 29 times the atmospheric pressure in psi times 0.031, which is the number of slugs to 1 pound, divided into the ideal gas law constant for air times the degrees Rankine absolute temperature. So the air density at that elevation and air temperature is 0.00229 slugs per cubic foot. Drag coefficient of this car is 0.33. Projected frontal area approximately 17 square feet. 70 miles per hour converted into feet per second, 102.7 feet per second. So all you do is multiply these four out. The drag coefficient times the air density in slugs per cubic foot times the projected frontal area in square feet of the automobile times the cruise speed in feet per second quantity cubed divided by 2. So it's 6,958 watts of power to overcome the aerodynamic drag. Divide that into 746. That would be 9.33 horsepower required to overcome aerodynamic drag. Next, calculate the power required to overcome tire rolling resistance. So we have a weight in pounds of automobile times the speed in feet per second times the coefficient of rolling resistance translates to 4381.2 foot-pounds per second of mechanical power. Divide that into 550 foot-pounds per second to 1 horsepower, 8 horsepower. So now if you add the two, it will only require 17.33 horsepower to keep the automobile moving, because the only forces opposing its inertia are the tire rolling resistance and the aerodynamic drag. So it takes considerably less horsepower to maintain steady speed compared to the acceleration. We know the MPG fuel economy rating for the car is 30 miles per gallon, highway at 70 miles per hour cruise speed with overdrive transmission. So for 1 hour if you drive 70 miles per hour, that would be 70 miles distance divided into 30 MPG. It will take 2.33 US gallons gasoline consumption per hour. Gasoline weighs 6 pounds per gallon, multiplied times 2.33 US gallons. So that's 14 pounds per hour of gasoline consumption divided by 60. That translates to 0.23 pounds per minute of gasoline consumption. 1 pound of gasoline equals 20,000 BTU, and 1 BTU per second is 778 foot-pounds per second of mechanical power. So, after overcoming the power lost to keep the engine running, power and heat lost out the exhaust, aerodynamic drag, tire rolling resistance, you're left with a usable power at the crank of 17.33 brake horsepower at given RPM, at given speed, to keep the vehicle in constant, steady cruise speed. Multiply times 33,000, divided into the pounds per minute gasoline fuel consumption times the BTU of gasoline per pound times 778. You divide these out, you get 0.16 times 100. 16% brake thermal efficiency is what you're actually dealing with when the automobile is moving at that speed. Now, if the speed was dropped to 60 and we recalculated, the brake thermal efficiency would be right around 24%. When the engine is idling at park and the automobile's not moving, it's around 32 to 33% brake thermal efficiency. So it's not just the power loss to keep the engine running, but the power to overcome the aerodynamic drag and the tire rolling resistance, which will cost fuel in order to allow that motion of the vehicle to occur. So 84% of the gasoline you put in your car is used to overcome the efficiency losses, and whatever you have in actual reality on the road is your 16%. So it should be known that the typical engine, when operating at idle, costs 1/3 of the fuel energy to heat the engine, 1/3 goes out the tailpipe in the form of waste heat, 1/3 drives the piston, and then you subtract from the 1/3 the power to overcome aerodynamic drag and tire rolling resistance when at cruise speed, and that's not including the higher horsepower requirements to accelerate the vehicle. So this is the actual real world calculation of an automotive piston engine, brake horsepower, foot-pounds torque, and brake thermal efficiency while in motion. Thank you for watching this video lecture, and have a good day.